Today we're going to learn about double angle, lowering powers, half angle, and product sum formulas for trigonometry. Sine of 2 theta is really just sine of theta plus theta. And I have an identity for sine of a sum. Sine of the first angle times cosine of the second plus cosine of the first times sine of the second. And look, these are like terms. So sine of 2 theta is the same as 2 sine theta cosine theta. We can do the same thing to find a double angle formula for cosine of 2 theta. That is equal to cosine squared theta minus sine squared theta. But sometimes it's helpful to be able to rewrite cosine 2 theta in just terms of sine or in just terms of cosine, not both cosine squared and sine squared. So let's write some equivalent expressions for cosine of 2 theta by plugging in our Pythagorean identities. Cosine squared theta is equal to 1 minus sine squared theta. So cosine of 2 theta could also equal 1 minus 2 sine squared theta. And sine squared theta is 1 minus cosine squared theta. Distribute the negative and combine like terms. So an equivalent identity for cosine of 2 theta would be 2 cosine squared theta minus 1. Do the same thing for tangent. That would equal 2 tangent theta over 1 minus tangent squared theta. And there are some double angle formulas. Number 1, if cosine of x equals negative 2 over 3 and x is in quadrant 2, find cosine 2x and sine 2x. Remember, x as the argument of cosine is talking about an angle. Draw the angle x and the reference triangle for it. We know that cosine corresponds to x over r, so the x value is negative 2 and the r value is 3. Use the Pythagorean theorem to solve for y. Because we're in quadrant 2, the y is positive, so y is positive root 5. I solved for the y value because I know I'm going to need it in the sine of 2x formula. But when finding cosine of 2x, I didn't actually even need to use the Pythagorean theorem because I already had cosine of x, and I know cosine of 2x in terms of just cosine. It's 2 cosine squared x minus 1. Remember, cosine squared theta would be the same as cosine theta squared, or cosine x squared, and cosine of x was negative 2 over 3, so substitute negative 2 over 3 and simplify. So cosine of 2x is negative 1 over 9. Sine of 2x means we plug in sine of the angle and cosine of the angle. Sine is y over r, so root 5 over 3, and cosine is what they gave us, negative 2 over 3. Simplify, and you get negative 4 root 5 over 9. For number 2, write cosine 3x in terms of cosine x. Well, cosine 3x could also be a sum of cosine, so cosine of 2x plus x. Use the sum formula, use the sum identity, so cosine of the first angle times cosine of the second minus sine of the first times sine of the second. Cosine of 2x could be rewritten as 2 cosine squared x minus 1. Remember, our goal is to just have everything in terms of cosine. Sine of 2x is equal to 2 sine x cosine x, so plug that in for sine of 2x. Now distribute the cosine x. You have 2 cosine cubed x minus cosine x minus 2 cosine x sine squared x. Oh my goodness, sine squared x, that's a Pythagorean identity. So substitute 1 minus cosine squared x so that our expression only has cosine of x. Distribute the negative 2 cosine x and then combine like terms. Cosine of 3x in terms of cosine x is 4 cosine cubed x minus 3 cosine x. Let's rearrange our double angle formula to get our lowering powers formulas. Cosine of 2 theta is equal to 1 minus 2 sine squared theta. Now solve for sine squared theta. Distribute that negative into the numerator, and sine squared theta is equal to 1 minus cosine 2 theta over 2. This allows you to write sine squared as an expression with trig where the highest power is 1. To create a relationship for cosine squared theta, rearrange cosine of 2 theta equals 2 cosine squared theta minus 1. And that is equal to 1 plus cosine 2 theta over 2. Now remember that tangent squared theta is equal to sine squared theta over cosine squared theta. That's a quotient identity, just being squared. Take the ratio for sine squared theta and divide the ratio for cosine squared theta. That's equal to 1 minus cosine 2 theta over 1 plus cosine 2 theta, which is the lowering powers formula for tangent squared theta. Number 3, express sine squared x times cosine squared x in terms of the first power of cosine. Sine squared x is just 1 minus cosine of 2x over 2. And cosine squared x is 1 plus cosine 2x over 2. Distribute the numerators of these fractions. Oh, that's difference of perfect squares. So I would just get 1 minus cosine squared 2x. I still have a cosine squared, so let's use the lowering powers formula again. Instead of cosine squared 2x, I plug in 1 plus cosine of 2 times whatever the angle was, which is 2x, divided by 2. A very common error would be to forget to double that 2x when you use the lowering powers formula again. So 1 over 4 minus, I decided to multiply the 1 over 4 times 1/2 so that I no longer have a fraction inside. So that's negative 1/8 times 1 plus cosine 4x. Now distribute the 1 over 8 so you can combine like terms. And then write your answer in factored form, so I took out the 1/8. But it wouldn't be wrong to write it in non-factored form. For half angle formulas, let's use our lowering power formulas first. Sine squared theta equals 1 minus cosine 2 theta over 2. What if we replaced theta with some angle divided by 2, a half angle? So I'll use u divided by 2. That would equal 1 minus cosine of 2 times u over 2 all over 2. So 1 minus cosine of u over 2. Now, if I wanted to solve for sine of u over 2, that half angle, I could just square root both sides. That means sine of u divided by 2 is equal to plus or minus square root of 1 minus cosine of u divided by 2. The signs, the plus or minus, depend on which quadrant u divided by 2 is in. So remember, sine is positive in quadrants 1 and 2, and cosine is positive in quadrants 1 and 4. Do the same thing with the lowering powers formula for cosine squared theta to get a formula for cosine of u divided by 2. So cosine of u divided by 2 is equal to plus or minus square root 1 plus cosine u over 2. Using the lowering powers formula for tangent squared theta, plug in u over 2 for theta and square root both sides. Guess what? We can actually simplify this further by multiplying by the denominator's conjugate, so we can use a Pythagorean identity. The numerator is now 1 minus cosine u quantity squared, and the denominator is now 1 minus cosine squared u, difference of perfect squares. 1 minus cosine squared u is sine squared u. Now, let's actually square root the numerator and the denominator. The square root of something being squared is equal to the absolute value of that something, because 1 minus cosine u was always being squared before being square rooted. And the square root of sine squared u is absolute value sine u, because cosine of u is always between -1 and 1, the midline plus the amplitude and the midline minus the amplitude. So that means that 1 minus cosine u will always be non-negative. Now we have to look out for the sign of the denominator, because that would affect the signs of tangent. But wait, the signs of sine u and tangent of u over 2 are actually always the same. Let me show you by drawing a quick sketch. Remember, tangent of u over 2 has a change in period. The new period would be pi over b, which is pi over 1/2, which is 2 pi. Hey, would you look at that? When sine is positive, tangent is positive. When sine is negative, tangent is negative. So because the numerator is positive and the sine of sine u will always be the same sign as the sine of tangent of u divided by 2, we no longer need our absolute value or plus or minus. The correct sign of your answer is already embedded into this ratio. We have an equivalent expression for tangent of u divided by 2 if we multiply both sides by 1 plus cosine u, the conjugate of the numerator. This allows us to use a Pythagorean identity to substitute sine squared u into the numerator, and then reduce sine of u over sine u, giving us two equivalent expressions for tangent of u over 2. This is helpful because sometimes the fraction for cosine u is more complicated, so we'd want that to be in the numerator, and sometimes the fraction for sine of u is more complicated, so we want that to be in the numerator. So the purpose of the two expressions for tangent of u over 2 is just to make reducing a little bit easier. Find the exact value of sine of pi over 8. Well, pi over 8 is not on the unit circle, but guess what? Pi over 8 is half of pi over 4, which is on the unit circle. So u, in this case, is pi over 4. To find sine of u over 2, pi over 4 over 2, I plug in pi over 4 for u. Oh wait, the answer is not plus or minus, it's only one of those. So let's figure out the sign by locating the quadrant that pi over 8 is in. You're looking at the quadrant of u over 2, not the quadrant of u. Pi over 8 is in quadrant 1, where sine and everything else is positive. So that's equal to positive root 1 minus cosine of pi fourths over 2. Cosine of pi fourths is root 2 over 2. Combine the 1 and the root 2 over 2 by getting common denominators. Instead of dividing by 2, multiply by 1/2, and you'll get 2 minus root 2 over 4, all under a root. Oh, convenient. The denominator is a perfect square, so we can just square root the numerator and the denominator separately, and we won't have to rationalize anything. So sine of pi over 8 is equal to root 2 minus root 2 all over 2. Number 5, find tangent of u over 2 if sine of u is 2 over 5 and u is in quadrant 2. First, let's draw the angle u and a reference triangle. Sine corresponds with y over r, so y is 2 and r is 5. Use the Pythagorean theorem to solve for x. Because we're in quadrant 2, x is negative. The formula for tangent of u divided by 2, we have two options. Which ratio is more complicated? That's the one I want in the numerator. Sine of u is 2 over 5, but cosine of u is x over r, which is negative root 21 over 5. So I want to use the first expression where cosine is in the numerator. 1 minus negative root 21 over 5 over 2 over 5. Combine 1 and root 21 over 5 by getting the same denominator. Multiply the numerator by 5 over 2, and you get tangent of u over 2 is equal to 5 plus root 21 over 2. And we have some more formulas that can be derived by our sum and difference formulas. Product to sum formulas allow you to write a product of sines and cosines as a sum, and sum to product formulas allow you to write a sum of sines and cosines as a product. Number 6, express sine of 3x times sine of 5x as a sum. So using u and v as our angles, u would be 3x and v would be 5x. Plug it into the formula. Now simplify. I do not want a negative inside of the argument of a trig function. But guess what? We have a negative angle identity. You could write that in factored form or distribute the 1/2. Number 7, write sine of 7x plus sine of 3x as a product. Using x and y as our angles for the sum to product formulas, X would be 7x and y would be 3x. You could rewrite it as u and v if you don't like the fact that we're mixing x's here. So sine of 7x plus sine of 3x is equal to 2 times sine of the sum over 2 times cosine of the difference over 2. Combine like terms and divide. Sine of 7x plus sine of 3x can be rewritten as 2 times sine of 5x times cosine of 2x. And there we have so many more trig identities or formulas derived from previously known trig identities.